All right, today we will talk about leverage. And leverage is an unusual observation in X. It's nothing to do with Y, it's unusual in X. If you remove 1 or 2 points and the conclusion changes, then the conclusion is sensitive to these points, and it should not be sensitive, it should be robust. And single observations that change conclusions are often unusual, and they are called outliers. There is, unfortunately, not a single definition of outliers. And today we will look at high leverage observations, and these are outliers in X space, not in Y, in X space. The estimated, emphasis on estimated, residuals are distributed with Gaussian with this standard error. We had seen that before. This comes from the head matrix, where this is the ith diagonal entry of the head matrix. And if you have large values here, then you will get a relatively small standard error. This leverage, so this H value is called the leverage. HII is the leverage of the ith observation. And it only depends on the X matrix, right? Because the head matrix is a function of the X matrix. So rather than trying to understand this based on the formula, let's look at an example. Here we have a data set with only one X variable. And we have one point that is unusual in X. Now, when you have only one X variable, unusual means it's either very large or very small, right? Because you have only one X variable, so there's no other dimension you can look at. So this is unusually large in X relative to the bulk of the observation. When you compute the leverage, meaning HII, for all observations, and then plot them again against X, so we can see which point corresponds to what, we see that the point over here that is unusual in X has by far the highest leverage. It's actually very large, it's 0.5. All the other observations have a relatively similar and relatively to this one low leverage. It makes sense that points that are at the edge of the cloud have slightly higher leverages than the adjacent points, and in the center you have the lowest leverage, right? So what happens if I take this point out because it has a high leverage and refit the regression line? Well, I take it out, refit the regression line, and what happens? Nothing, or pretty much nothing visible to the eye. So just the fact that the point has high leverage doesn't mean that it will affect the regression line and analogously the regression coefficients. So high leverage means it's unusual in some way. We should look at it. Maybe there's trouble down the road, but it's not necessarily trouble. Here's another observation that has no leverage, basically. You have the X values quite distributed across the range shown here, and then in the middle there's an X in here. That has no leverage because leverage doesn't take into account Y. We're just looking, is this an unusual X value? And no, it isn't. It's just in the middle here, right? So it's not an outlier in X space. It is, of course, possible to have a value that is an outlier in X space, so has high leverage, and also has quite a high residual. And if you leave that point out and refit the regression line, so high leverage and high residual, then the regression slope changes by quite a bit. So a high leverage point, when paired with a high residual, can really have a strong effect. So going back to that formula, high leverage means a high value of HII. So observations that have high leverage, 1 minus a fairly large value, means this is fairly small, really. So high leverage values have small standard errors. That may well seem counterintuitive. The intuition is as follows. Going back one slide, a high leverage observation has the ability to pull the regression towards it, right? So here we have the regression line, and by adding a high leverage observation, we have the potential to pull it towards it, or the ability to pull it towards it. So I call that gravitational pull. And this gravitational pull is consistent with the idea of being quite certain, meaning there being a small standard error for this particular observation. It's intuition, it's not a proof, but that might explain it. All right. So we have looked at high leverage just for one X variable. So what is an outlier in X space when there's more than one X variable? Well, just looking at one, sort of a house with 20 bathrooms in a sample where all other houses have 1 to 4 bathrooms might be unusual, right? It might not be wrong because maybe you're sampling in London and you've got Windsor Castle, but it's definitely something that, you know, surprises you. When you have more than one X variable, it doesn't necessarily mean that high leverage corresponds to a high value in any one dimension. It could be an unusual combination of values. So, for example, a house with 3 bathrooms that only has 1,300 square feet might be a high leverage observation, but 3 bathrooms by itself is not that unusual. 1,300 square feet by itself is not unusual. It's just a smaller house, a townhouse maybe. But a smaller townhouse with 3 bathrooms, that's unusual. And yeah, so that would be an example of a leverage with more than one variable. So we are looking at diagnostics, and all of these things are plots. So we're looking to plot high leverage or the leverage against something. So far we've plotted against the X variable, but there was only one. When I have more than one X variable, that's not the right way to go. So I have to order them in some point. So I could make a sequence of the data points from 1 to n. If I have taken the observations over time, I could plot them over time. I could also plot them against something else like fitted value or something, just to get some order out of it. It doesn't matter a lot. You're just trying to identify. Now, what does this mean for a plot? How do I interpret it in practice? What are large values? There is, unfortunately, again, there is no cutoff where you have to say, okay, which is larger than that, then it's high leverage. Maybe 0.5 is large. I found that value somewhere written down. But if you look at this plot, for example, well, we don't reach 0.5, but also there's nothing unusual. I'm interested in seeing whether there's a couple of leverage points that are much different than the others. And there's the largest leverage point, but every plot has one. But it's not unusual, so there's really nothing to look at. If we find a high leverage point, we want to look in our data and see why it's high leverage. Of course, maybe we learn something. We learn something about the structure of the data, or we might even find an error. So here's some R code, how to do the leverage plot. I once did a leverage plot where I found a typo in the housing data set. And I regressed the house price on the number of rooms, I think, and I found this leverage plot, and this point sticks out, right? It's not 0.5, but it sure sticks out. So you want to look at that. And then it turned out the reason why it had a high leverage is because this house indeed had 20 rooms. Now, this house was not Windsor Castle, and so it turned out to be a typo. Changed and looked at the original source of the data, changed the number of rooms, and we had something regular, just a regular 2 rooms or something like that. Yeah, 2 rooms. Okay, that is the end of this segment for the leverage.